yeah, I'll speak about how adjoint models and uncertainty quantification can help us to design observing systems. And yeah, as Danny said, this was part of my PhD work and also my first postdoc year at UT Austin together with Patrick Heimbach. Okay, so I think this crew here agrees with me that ocean observing systems are absolutely crucial for understanding the ocean's role in climate. But at the same time, they're also very difficult and expensive to build and maintain, right? So a great example is the OSNAP observing system in the North Atlantic. So this is a huge and costly international effort, but over the last few years, it has led to revolutionary new insights into North Atlantic ocean circulation. So in this talk, I want to discuss one way in which ocean models can inform effective observing system design. And the overarching idea is simple. We want to take advantage of oceanic teleconnections that propagate observational constraints over long distances. And in this talk, I will use examples from the North Atlantic. But yeah, I would be excited to talk about the Southern Ocean with you guys in the discussion session afterwards. So here's the outline of my talk. So first I'll talk about oceanic teleconnections in the North Atlantic, then, and yeah, how they can be systematically uncovered with adjoint models. Then second, I'll introduce the concept of dynamical proxy potential. And then third, I will discuss how teleconnections and dynamical proxy potential can be used to design observing systems. Okay, so let's start with looking at some oceanic teleconnections in the North Atlantic. So I'll show you two perturbation experiments with MIT GCM. In the first experiment, I will perturb wind west of Iceland, here in this first green box. And in the second experiment, I will perturb wind west of Africa in the second green box. And in both experiments, we'll be interested in how the North Atlantic circulation and temperature react to these wind perturbations. And in particular, we'll be interested in how two things are impacted. First, subsurface temperature here in the Irminger Sea at one of the OSNAP moorings, shown by this yellow dot. And second, heat transport across the Iceland-Scotland ridge, shown by this yellow line. Okay, so experiment number one, I will perturb wind in this green box. And the red and the blue arrows here show warm and cold ocean currents in the North Atlantic. So let's see what happens. If we increase the northward wind in this green box, the ocean flows east, we get Ekman onshore convergence and a positive pressure anomaly along the Icelandic coastline. And this sets up an anomalous pressure gradient, which spins up an anomalous clockwise circulation around Iceland, as shown by these black arrows here. And this anomalous circulation pattern will then weaken the Norwegian Atlantic current. And at the same time, it will also weaken the East Greenland current. So how does this flow affect temperature at 300 meters depth in our model? Well, as predicted by the mechanisms that I've just shown you, there is a cold temperature anomaly propagating into the Norwegian Sea due to a weakened warm Norwegian Atlantic current. And at the same time, there is a warm temperature anomaly propagating into the Irminger and Labrador Seas due to a weakened cold East Greenland current. So to summarize, wind west of Iceland drives an anti-covariation between Iceland-Scotland ridge heat transport and Irminger Sea subsurface temperature due to a shared adjustment mechanism. And we'll come back to this later, but let me show you the experiment number 2 first. So in this experiment, we will perturb wind west of Africa, and it is useful to first look at the response in bottom pressure. So increasing the northward wind in this green box again, leads to ocean to Egmont, to eastport Egmont transport and a positive pressure anomaly along the West African coast. And this pressure anomaly gets rapidly propagated cyclonically around the North Atlantic basin through coastally trap waves. This sets up a pressure gradient, an anomalous pressure gradient between the Nordic seas and the North Atlantic. And this pressure gradient spins up the subpolar gyre. So we can now look at the response in subsurface temperature. So at low latitudes, we see the effect of baroclinic Rossby waves that propagate temperature anomalies from the eastern boundary westward. But further north, we see a warming of the entire subpolar gyre, including a larger heat transport across the ice in Scotland Ridge. And this high latitude warming is explained by the spin up of the subpolar gyre. So to summarize, wind west of Africa drives a covariation between Iceland-Scotland Ridge heat transport and Irminger Sea subsurface temperature, again, through a shared adjustment mechanism. So now we have seen two examples for what can drive covariation or anti-covariation between Irminger Sea subsurface temperature and Iceland-Scotland Ridge heat transport, right? Wind west of Iceland and wind west of Africa. But how can we identify all such possible causes of covariation? And this is where the Adjoint model comes into play. So what does it mean to run an Adjoint model? You can essentially think of it as running a perturbation experiment backwards. So far, I've only shown you classical forward perturbation experiments. And in a forward perturbation experiment, you perturb one variable at one location, for example, wind west of Iceland. Then you run your standard forward model, the MIT GCM, and then you obtain the response in all output variables, right? Temperature, bottom pressure, and so on at all locations. An Adjoint model works the other way around. You tell the model which output variable you're interested in, for example, Iceland-Scotland Ridge heat transport. And you can only choose one such variable per Adjoint model run. Then you run your Adjoint model, which is essentially running your model backwards. And then you obtain the linearized sensitivities to all input variables. And these sensitivities tell you all possible causes that could lead to changes in Iceland-Scotland Ridge heat transport. So I've run the Adjoint model twice, once for Iceland-Scotland Ridge heat transport and once for subsurface temperature in the Irminger Sea. And these two figures show the result. So these figures show the sensitivity of heat transport across the Iceland-Scotland Ridge and Irminger Sea subsurface temperature to meridional wind stress. And we immediately notice that both of these metrics show sensitivity to wind west of Iceland and wind west of Africa, as we expect this after these forward perturbation experiments that I've shown you earlier, right? And we also see that the sensitivity to wind west of Iceland is of opposite sign, while the sensitivity to wind west of Africa is of equal sign. And that is totally consistent with this anti-covariation and covariation that we've observed earlier in the forward perturbation experiments. So the nice thing about the Adjoint now is that it tells us about all sensitive spots, not just the two that I tested in the forward perturbation experiments. So we can roughly identify two regions where both of these metrics show sensitivity. So in box 1, sensitivity of opposite sign, and box 2, sensitivity of equal sign. And the underlying mechanisms are very similar to the ones that I've shown you in the movies. So now that we know how to identify all possible causes of covariation, we can investigate dynamical proxy potential. So in oceanography, we often look for proxies, right? We want to take observed quantities, salinity, temperature, velocity at certain locations and ask, can we use them to infer other quantities of interest that might be much harder to observe or maybe impossible to observe, such as ocean transports or future sea level rise or anything like this. And conventionally, proxy potential is used or is assessed by using statistical tools, for example, correlation. Statistical tools are often super useful, but the problem is that they do not guarantee causation, only covariation. So there are many examples for spurious correlations, and one is shown here on the right, namely that the divorce rate in the US state Maine correlates with the per capita consumption of margarine. So the correlation, the R squared is 0.99. So in this talk, I want to investigate the dynamical proxy potential, or DBP, and this DBP quantifies only physics-based covariation, so covariation that has dynamical underpinnings. And it is computed with the Adjoint model, and it is essentially the dynamical analog to the statistical R squared. So let's apply this concept of dynamical proxy potential to the example that we've looked at in the first part of the talk. So let's say our quantity of interest is heat transport across the ice in Scotland Ridge, and we have an observed quantity by OSNAP, namely subsurface temperature in the Irminger Sea. So now we can ask, what's the dynamical proxy potential of our OSNAP observation for our transport quantity of interest? And to compute this DBP, we basically compare these Adjoint sensitivity maps that we've seen before. So more specifically, we compute the squared dot product of these sensitivity maps. So how is this dot product taken? You multiply the normalized sensitivities grid point wise and add everything together. So grid points in box number 2 lead to a positive contribution, while grid points in box 1 lead to a large negative contribution. And then, adding these two values and squaring, the result gives us a value of 19%. So what's worth noting here is that the DBP takes into account constructive versus destructive interference of this covariation versus anti-covariation, right? So let's summarize what we've seen so far. So we've looked at large-scale oceanic teleconnections driven by wind along the northern and eastern boundary of the North Atlantic, and these teleconnections lead to physics-based covariation. And this physics-based covariation we have quantified by dynamical proxy potential. So in our case, we found a value of 19%. So you might say, well, 19%, that's actually not a very high value, right? Or not high enough to be useful. But we have to keep two things in mind. So the first one is, right, this DBP quantifies only physics-based covariation. So there's nothing like statistical significance tests that have to be passed. So every value above 0 basically means that our observation contains some constraint for our quantity of interest. And the second thing is, well, how great would it be if our OSNAP observation here would tell us 100% about the heat transport across the ice in Scotland Ridge 100 kilometers away, right? That's actually not what we expect. So now the key now is to combine the information from multiple observations to bump up this value of DBP from 19% upwards. And this is exactly what the last part of my talk is about. So we want to generalize this DBP to multiple observations while taking into account that there might be some data redundancy across multiple observations. Okay, so to work toward observing system design, we will reinterpret the things that I've shown so far in the talk in a different context, namely in the context of uncertainty quantification and ocean state estimation. And I will I only have 4 or 5 minutes left, so I won't go into any technical details. Those can be found in our 2021 James publication. I'll only mention a few things. So first, in the UQ framework, adjoint sensitivity maps are something like rotated Hessian eigenvectors in a mathematical vector space, the control space. And then the DBP being 19% can be reinterpreted as follows. It means that adding our OSNAP observation without noise to the ocean state estimate will reduce the uncertainty in our quantity of interest by 19%. So a nice property of this DBP calculation is that we don't need the actual data. So in this example, we do not need the actual temperature value that the OSNAP mooring measures, right? All we used was the adjoint sensitivity maps that were computed through, by uncovering dynamical relationships in the model equations. So that means that we can assess DBP and uncertainty reduction for future observations before putting any instruments in the water. So within this UQ framework, we can now assess data redundancy. Let's say we're thinking about putting a mooring into Denmark Strait here at location D. So here on the right, you see the adjoint sensitivity map of subsurface temperature in Denmark Strait. And you see it looks very similar to the Irminger Sea sensitivity map that we've seen earlier, right? And that means that the Irminger Sea and Denmark Strait observations, they contain quite a bit of redundant information. And we can formally assess this data redundancy by viewing these sensitivity maps within this mathematical vector space that I've mentioned on the previous slide. So in this vector space, we can orthonormalize vectors, which corresponds to removing redundant information. So if we do this, we get a sensitivity map like this, right? You see that a lot of the sensitivity information of the Denmark Strait observation got removed because it was redundant. So now we can combine multiple observations and ask, what is their combined information content, or what is their combined uncertainty reduction that they would imply? And that's plotted here on the right. So we've seen that the Irminger Sea observation alone would lead to an uncertainty reduction by 19% in our transport quantity of interest. So here we see that the Denmark Strait observation alone would lead to an uncertainty reduction by 30%. And then both observations combined lead to an uncertainty reduction by 30% as well, right? Which is less than the sum of 19 plus 30%. And this is due to the data redundancy that we've already seen on the previous slide. So in summary, adding the Irminger Sea observation to the Denmark Strait observation gives no extra information in this example due to data redundancy. If we instead had considered adding a mooring here close to the Portuguese coast, right, at location B, we would find that the Irminger Sea observation A and the Portuguese coast observation B, they're very complementary in their information content. So again, I'll just mention that, right, the actual data is not needed to assess this data redundancy versus complementarity. So we can test it for future observations. Okay, so let me just sum up briefly. So at the center of my talk was the Adjoint model, and the Adjoint model produces sensitivity maps like these, right? And these can be interpreted in two ways. So first, these sensitivity maps systematically uncover oceanic teleconnections and shared adjustment mechanisms. The second interpretation is that they are the main ingredient into an uncertainty quantification framework within which we can assess data redundancy. So these two interpretations together give us a means for both dynamics informed and quantitative observing system design. So a limitation is that the Adjoint only provides a linearized approximation of the ocean dynamics, right? So what I've shown today, this approach is appropriate for capturing large-scale dynamics and Gaussian approximations of uncertainty. So I see this method as one tool of many in a big toolbox, and we probably need the full toolbox to tackle this really hard problem of how to design the best or the most effective global observing system. Cool, thanks.